Hello everybody, this is a lecture on the two-body central force problem, the first of the lectures. And here we are now going to apply all that we have learned in Lagrangian mechanics, many aspects of it, into a single problem. And it's a basic, one of the very basic and fundamental problems, and one of the problems for which the Lagrangian mechanics was developed. Okay, so let us start. So let us start by specifying what is the problem. So I have two bodies and there is no external force here. Everything is between these two bodies. And so say you can consider one as mass m1, other as mass m2. And the only type of force by which they interact is a force which is central, which depends on the distance between these two. So if I can write a potential for this force, the potential will depend on, so let us start by choosing the Cartesian system. So I denote Cartesian system this way, x, y and z, and the radius vector to this I call x1 and the radius vector to this I call x2. So this force is always given as x1 minus x2, mod of that. Okay, so this is the potential for the central force. Okay, it depends on mod as we have showed here, and depends on only the distance between them. So that's the potential. What's the kinetic energy? So this is V, and you see that it is 1 by mod x1 minus x2 if it is gravity for a single particle of these particles, but it can be many things in general. And the kinetic energy is simple, half m1 x1. So let me write in vector form for the time being, plus m2 x2 dot square. So I write the Lagrangian. This is the first time I am writing the Lagrangian for this problem, and you will see how the Lagrangian will evolve. And then minus V mod x1 minus x2. Looking at this Lagrangian, it's a function of 6 variables. This is a function of 6 variables. And if I look at the Lagrangian at this form, you see these are like, so what is this? So let me write this explicitly. This is essentially x1 minus x2 square plus y1 minus y2 square plus z1 minus z2 square, and you see that you see immediately that all the coordinates, all the 6 coordinates are present in the Lagrangian. There is no cyclic coordinate, right? But I can write this Lagrangian in a little different form. So let me try to do that. This you have done in your class 2. This is called the center of mass coordinate system. So I defined a capital R, which is x1 plus x2 by 2. So essentially goes up to the middle of this bar. So that is capital R. Well, actually, I must be careful because they have different masses. I define it to be the center of mass coordinate. So I don't have that x1 plus x2 by 2, but rather m1 x1 plus m2 x2 by m1 plus m2. And I define small r as simply mod x1 minus x. Okay, so let me not define mod here. So it's x1 minus x2. You can as well define x2 minus x1. That's all right. If you do that, then I can rearrange these. So check, you can write it this way. You can just not doing the intermediate steps, but you will see that I can write this in the following way. Half capital M, I will define what it is, r dot square, plus half small m, small r dot square, minus v of mod r. Okay, and so let me define for you that small m is the reduced mass and capital M is the total mass. I said reduced mass, I wrote something else. So this is m1 m2 by m1 plus m2. This you can see easily. The easiest way to verify is that put everything back in this expression, you will be getting back that equation. Okay, but that this is the second incarnation of the Lagrangian for a central force problem, and you immediately notice something. What do you notice? I have a cyclic coordinate. The Lagrangian does not depend on r explicitly, capital R. So I have a corresponding canonical momentum, which I call P capital R, that is del L del mr, del L del r dot. Del L del r dot is nothing but mr dot. And I use Raoult's prescription to write a modified Lagrangian, the third incarnation of the Lagrangian, and this is the old L. So let me just write this with a bar, which I will remove later on. This should be this minus. If you remember, just go through the go look at the Raoult's prescription that you have learned. So PR R dot. Now, if there is an external force is being applied on this system, then obviously this doesn't contain the external force. If I apply an external force, it will change r dot. Otherwise, we know that it will stay where it is. So you can guess what L bar can be. So my modified Lagrangian now only have smaller. So this is half m r dot square. I did not work out through here, but that is all right. And then mod r. So this is at this stage, this is my modified Lagrangian. Okay, so let us go one step further now. Now, this step can be done in many different ways. I will bring to you an argument and try to reduce the dimensionality of this Lagrangian. You see that I still have this written as in terms of vector r, so which means I have three coordinates. Okay. Now, because I have the motion of a thing, so now one thing has happened is that I am defining only one r, so you can think of this as one particle moving in that central force. The motion of these two bodies has reduced to the motion of a single body. Actually, the motion of the other body is also there. The motion of the other body will give you m r dot is constant, so which I am not writing explicitly, because this equation is trivial to solve. Once you know what is r dot, it will stay as it is because m is constant. So this will only change the vector r as some constant times time. So we are looking at the rest of the Lagrangian. So there is a part which is depends on m r dot, m capital R dot, which we are not interested in right now or any further. So this is the remaining interesting part. And it still has 3 coordinates. So because it's a motion of a single particle, what are the initial conditions? Well, you will argue the initial conditions are nothing but r at t equals to 0 and r dot at t equals to 0. These are the two initial conditions, right? Now, if these are the two initial conditions, then there are two vectors. So I can draw these two vectors. So I draw one r and one r dot. Okay, and in most general case, they will not be collinear. So I have drawn them separately. Now I have drawn them this way, but you may ask the question that how can you be sure that they will be in this plane? Well, I am always sure that will happen. If you think of two non-collinear vectors, they will always define a plane. You may do a little simulation in your head and make sure that works out. Now, if that is true, then what do I know? I know that the particle is on this plane where I have drawn these two vectors, somewhere on this plane, and the position of the particle is given by this vector, and it can change from this position. So if this is my origin, this is the radius vector, the particle is here now, it can go anywhere. Maybe it can go out of this plane. And what will that depend on? It will depend on the velocity at that particular time. So if the particle is here, the particle is, there is no force, it will move this way because that is the direction of the velocity. But there is a central force, right? It may change the direction. But you remember that because it's a central force, it only depends on r. It depends on r. And r is this vector. So it depends, the direction of the central force is also along this vector. That is the definition of this. That's what we mean by central force. A force which has the direction along the radius vector. That's called a central force. So because the direction is along the vector, it's along this plane. So the force can change the motion only along this plane. So its original motion, which is given by r dot, is in this plane. And the force can change its motion only along this plane. So the vector, the final vector, wherever it is after time t, so this is, I am drawing now r at t equals to t plus delta t, it will be in that plane. So the particle can only be in that plane. And now you can argue this way. If you simulate the next time step, you will again see the particle will stay in that plane. So that essentially means that this particle will always stay in this plane. Okay, and that tells you that now this comes from a symmetry in the Lagrangian, which I am not exploring directly. So you can now look at that symmetry, and that symmetry is coming from the fact that r is a function of the vector r. The potential is a function of the vector r. And what it does is that it conserves the angular momentum, and that is easy to see. Angular momentum L is nothing but moment of the linear momentum, which is r cross r dot, m r dot. So if I calculate the time derivative of L, it is, the first term will be the dot product of that plus r cross m r double dot. Now the dot product along the same direction is 0, so r dot cross r dot is 0, and then m r dot is nothing but the central force, which is some force times r cap, and then r cap and r has the same direction, so this is also 0. So this conserves the angular momentum. Now this is essentially coming from the fact that FR, this force is FR cap, which is coming from the fact that the potential depends on the modulus of R. Okay, so this is the statement of the conservation of angular momentum. What can we do with it? Instead of writing the vector R in terms of 3 components, we can now write it in terms of 2 components, and the obvious choice of the polar coordinate system, 2D polar coordinate system. So my L now becomes half m r dot square plus half m r square phi dot square minus v of r. What do you see? You immediately see that there is no phi dependence, which means that p phi is constant. Let us call that L0. So I get another cyclic coordinate, phi is cyclic, and the corresponding canonical momentum p phi is constant. So what is p phi? P phi is m r square phi dot. So this is equals L0. So I can figure out what is phi dot square will be L dot square by m square r to the 4. Now I need to use Routh's prescription explicitly, so let me do that. So let me change. So what we have done, so we have found that phi is cyclic. This is another incarnation of the two-body central force problem, effective Lagrangian. And I have found phi is cyclic, and I have correspondingly I have defined p phi equals L0. So L0 is the constant. Remember, we called them like C constants when we discuss Routh's prescription. So I have to now change L to L bar. Again, I will write that as L, which is minus L0 times phi dot. So let's do that. So this is half m r dot square. In the second term, I will replace phi dot in terms of L square. So this will be L naught square by m square r to the 4. And then I have L naught phi dot, so which is L naught phi dot. So L naught square by okay. So phi dot is L naught by m r square. So this is m r square. And then I have the potential V as a function of r. If you work out a little bit, so this m cancels with that, I am left with 1L, so this becomes r square, and then this has a plus sign, this has a minus sign. I can write my Lagrangian, now this I am writing this one here, as half m r dot square minus, now I club these two together, so this is Vr minus plus L naught square by 2mr square. Okay, so I have combined this term with this. Now this Lagrangian now has only one coordinate, which is r, and this entire thing I call as effective potential, right? So because it's a function of r and this is the kinetic term, so I can think of now an equivalent one-dimensional problem where I have only one kinetic term, half m r dot square, which looks quite like half m r dot square has the like half m x dot square, like Cartesian, and then I have a particular potential. So it's a one-dimensional problem. You will always agree that one-dimensional problems are the easier problems to solve. But you remember that with this I have a few other things. I have phi dot, which is given here. So L naught by mr square, L naught by mr square. So phi dot does change with r, but if I calculate how r changes with time by solving the Euler-Lagrange equation corresponding to this, then obviously I can just use that r as a function of time here and integrate phi dot over time. And I also had r dot equals another constant, let's call that n, r naught by m. So these are three equations. This is four equations. One equation, this is four equation. Then I have, remember, I had one constraint that the total angular momentum is conserved. That is fifth equation, and the sixth one is this. So I have total six, three here, one here, total angular momentum conserved, that is one, and one here. So total six, and I started with six. So this is the sixth equation. But the only thing that I should bother about now is this one. And you can calculate the Euler-Lagrange equation corresponding to this, which I will not do, because we will look at the problem in a little different perspective. We will use the, if you remember, Barthami identity, which gives you the total energy. In this case, the total energy is also constant. So we'll use that information to work out this problem further. And we'll see that there are other hidden constants in the two-body central force problem. Okay, thank you for today. Bye.